Hey everyone, and welcome to this explainer. Today, we're going to tackle one of the absolute most classic problems in computer science and programming, the n-queens problem. Just imagine you have an n by n chessboard, and your job is to place n queens on it so that absolutely no two queens are threatening each other. Now, if you know chess, you know a queen can move any number of squares vertically, horizontally, or diagonally. So our goal here is to place all these queens perfectly safely. And this isn't just a fun little puzzle, it's actually a fantastic hands-on way to really understand backtracking. That's a fundamental algorithmic technique used in everything from solving Sudoku puzzles to optimizing really complex logistics. And the best part? We're going to implement the whole thing in Python, step by step, breaking it down so it makes complete sense. Let's get right into it. Here is our roadmap for today. First, we'll outline the n-queens problem. Second, we'll look at exactly why backtracking works. Third, we'll build a recursive solution in Python. Fourth, we'll try out an iterative approach. And finally, we'll wrap up by comparing the algorithm complexity. Okay, part 1, the n-queens problem. Let's start by defining our constraints really clearly. How exactly can we place n queens on an n by n chessboard so that no two queens attack each other? Well, if we were to just place them randomly on, say, a 4x4 board, we'd quickly run into conflicts, right? Queens in the exact same row, column, or diagonal will immediately attack each other. So because of how queens move, we have 3 fundamental rules. We can only have exactly 1 queen per row, exactly 1 queen per column, and no two queens can share the same diagonal. Basically, we can't just guess blindly. We're essentially looking for a perfect sequence, a permutation of column positions for each row while carefully making sure no diagonal paths cross. Oh, and here's a quick fun fact for you. Solutions actually exist for all board sizes n, except for 2 and 3. You literally just can't make it work on boards that tiny. But for a standard 8x8 chessboard, there are exactly 92 unique safe configurations. Now, finding all 92 manually would take absolutely forever, which is exactly why we're going to use code. Moving on to section 2, why backtracking works. So why exactly is backtracking the go-to method for this, instead of just brute force guessing? To put it simply, backtracking is a systematic way to explore all possible solutions. You build them one piece at a time, and, this is key, you completely abandon paths that can't possibly lead to a valid solution. Think of it like navigating a giant maze. You walk down a path, and if it leads to a dead end, you fail fast, you step back, and you try another route. For our board, we place queens row by row. If a placement is safe, awesome, we move to the next row. If we get stuck, we just step back and try a different spot. This concept is absolutely crucial because it mathematically saves our computers from just totally freezing up. By failing fast and ensuring only 1 queen per row, we prune the search space incredibly early. Think about it this way. If we used a naive brute force search on an 8x8 board, we'd have to check 8 to the power of 8 combinations. That is over 16.7 million states. No thank you. But by utilizing backtracking and placing exactly 1 queen per row and column, we reduce those astronomical calculations down to a much more manageable factorial scale. 8 factorial is just 40,320 permutations. I mean, that is a massive optimization. It's a total game changer. Okay, section 3, recursive solution in Python. Let's actually start building the code. Honestly, this is the most intuitive way to implement this, because it closely mirrors how we'd physically solve the puzzle in real life. Before we dive into the actual Python syntax, let's manually trace a 4x4 board step by step so you can see it in action. We start at row 0 and place a queen at column 0. Looks safe. We drop to row 1. Now, column 0 is blocked, column 1 is a diagonal conflict, but hey, column 2 is safe. Let's place it. Down to row 2. Columns 0, 1, and 2 all have conflicts, but column 3 is safe. Finally, down to row 3. We check the spots and boom, column 1 is safe. We did it. We found a perfect sequence. Columns 0, 2, 3, and 1. We just built a solution vector. So how do we represent this board efficiently in Python? Actually, scratch the idea of a 2D matrix. We really don't need it. We can just use a highly efficient 1D list. We'll initialize it using standard Python syntax, by multiplying a list containing a -1 by n. In this list, the index represents the row, and the value stored at that index is the column where the queen sits. So an array of 4 -1s is literally all you need to track a 4x4 board. Pretty neat, right? Now, let's talk about our isSafeHelper function. Checking for vertical conflicts is a breeze. You just check if the column is already in our list. But what about checking diagonals? Well, we use this brilliantly simple math equation that maps perfectly to the physical diagonal movement of a chess piece. Two positions are on the same diagonal if and only if the absolute difference in their columns equals the absolute difference in their rows. If those absolute values match up, you've got a diagonal collision on your hands, and our code knows instantly to skip that spot. And here is the core recursive function that ties the whole shebang together. It simply loops through the available columns for the current row. If our isSafe function returns true, it drops down a row by calling itself. That's the recursion. But here's where the backtracking magic happens. If it gets stuck and that recursive call returns without finding a solution, it intentionally unplaces the queen by resetting the board at that row back to -1. It cleans up its mess, backtracks up the call stack, and just tries the next column in the loop. Let's look at section 4, the iterative approach. While recursion is elegant and honestly mathematically beautiful, it's definitely not the only way to do this. Let's explore an alternative, non-recursive implementation. This iterative method mimics the exact same depth-first search logic we just talked about, but it uses a manual data structure. You might be wondering, why do this? Well, recursive functions use the program's built-in call stack, which has a strict depth limit. If the board is huge, recursion might crash. By using an explicit manual stack, we completely bypass those limits. We basically store the current state as a little package, the current row, and the current board state. The implementation for this relies on a simple while loop. As long as our manual stack isn't empty, we pop off a state, check the safe columns for that specific row, and then for every safe column we find, we push a brand new updated board configuration back onto the top of the stack for the next row. It's really cool because we achieve the exact same depth-first exploration, but with explicit granular control over the memory. Moving right along to section 5, comparing algorithm complexity. With both of these code implementations under our belts, it is absolutely crucial to understand how they stack up against each other. Let's look at the computer science behind the execution. If we compare the stats side by side, whether you use the recursive approach, the iterative approach, or even a highly advanced bitmask technique that uses integer bit shifting for maximum speed, the worst-case time complexity remains strictly exponential. It's O of n factorial across the board. The problem just naturally grows that fast. However, space complexity is an incredibly lightweight O of n for all of them, mainly because we're only storing 1D arrays and stack depths equal to the number of rows. Ultimately, the recursive way is by far the easiest for beginners to grasp, while the iterative method is a fantastic intermediate step to really deeply understand depth-first state management. To wrap up this explainer, I want to leave you with a coding challenge. Based on everything we just learned about how this algorithm explores the search space, how would you tweak our Python code so that instead of finding all 92 solutions for an 8x8 board, it immediately halts and returns upon finding the very first one? Think about how you could bubble a true flag all the way up that recursive call stack. Drop your ideas and solutions in the comments below. I can't wait to see what you come up with. Thanks so much for learning with me today, and I'll catch you in the next explainer.